Look at almost any major city in the world. London, New York, Shanghai, Dubai. Different countries, different cultures. But underneath many of those spectacular skylines is the same hidden idea: a skeleton made of steel. Before steel, buildings were largely limited by the strength and weight of stone, brick and timber. The taller you built, the heavier the walls became. Then something changed. Engineers discovered that instead of making the walls carry the entire building, they could make a skeleton carry it. And suddenly, cities could grow upwards. This is the story of structural steel, and how one material changed the way humanity builds. Before steel, there was iron. Before skyscrapers, there was another revolution: iron. In 1779, the world's first major iron bridge opened at Coalbrookdale in England. Cast iron could carry enormous compressive loads, making it useful for columns and arches. But it had a weakness. It was relatively brittle and performed poorly when subjected to tension or bending. Engineers therefore increasingly turned to wrought iron, which was more suitable for structural members such as plates, ties and beams. Then came one spectacular demonstration. London's Crystal Palace, built for the Great Exhibition of 1851, used an enormous iron and glass structural system assembled from manufactured components. Humanity was discovering something important. Buildings could be engineered from components rather than simply built as massive walls. But the real revolution was still coming. The invention that made steel possible. Steel wasn't new. Cheap steel was. For centuries, people had produced steel. But producing large quantities economically was another problem entirely. Then, during the Industrial Revolution, new steelmaking processes transformed production. The Bessemer process of the 1850s was particularly important because it made it possible to produce large quantities of steel much more efficiently than earlier methods. Suddenly, steel could move from being an expensive specialist material towards becoming an industrial building material. And steel had a remarkable combination of properties. It could resist tension. It could resist compression. It could resist bending. And engineers could calculate its behavior with increasing confidence. That changed the question. Engineers were no longer asking, "How high can this wall go?" They were beginning to ask, "How high can this skeleton go?" That distinction would transform architecture forever. The building that changed the skyline. Imagine removing the weight from the walls of a building. That's essentially what the structural skeleton made possible. The home insurance building in Chicago, completed in 1885, became a landmark in the development of modern skeleton frame construction. Instead of relying entirely on massive load-bearing masonry walls, much of the structural load was carried by an internal metal frame. The result? Walls could become lighter. Windows could become larger. Interior spaces could become more flexible. And buildings could rise higher. The skyscraper was no longer just an architectural dream. It was becoming an engineering possibility. And the idea spread. Steel frames began transforming cities around the world. But there was a hidden problem. The secret isn't the steel. It's the connections. Here's something most people never think about when looking at a skyscraper. The steel isn't working alone. The connections are doing just as much work. Early steel structures often relied on bracing to resist horizontal forces such as wind. But engineers began developing increasingly sophisticated connections between beams and columns. Rivets connected structural members. Later, welding allowed steel components to be fused together. Bolted connections became increasingly common because they could be manufactured and assembled efficiently. And engineers developed moment-resisting frames, where beam-to-column connections can transfer bending moments and help the frame resist lateral forces. The idea is surprisingly simple. When wind pushes a building sideways, the frame must resist that movement. The columns and beams bend. The connections transfer forces. And the entire structure works together. Modern continuous steel frames can therefore resist vertical loads and lateral forces through frame action, although many buildings combine moment frames with bracing or other structural systems for efficiency. So the next time you see a steel skyscraper, don't just look at the beams. Look at the joints. Because sometimes the smallest part of a structure carries the biggest responsibility. When the earth tested steel, engineers thought they were getting very good at building with steel. Then the earth tested them. Earthquakes are among the most demanding challenges a building can face. A structure isn't simply pushed down. It is shaken sideways repeatedly and unpredictably. Steel's flexibility can be a major advantage, but the behavior of its connections is critical. Then came January 17, 1994. The Northridge earthquake struck Southern California, and engineers discovered unexpected damage in welded steel moment frame buildings. Fractures occurred in beam-to-column connections across the affected region. Subsequent investigations found that connection performance depended on a complex combination of structural characteristics, construction and inspection quality. This was a profound lesson. The problem wasn't simply, is steel strong enough? The better question was, how does the entire structural system behave when pushed beyond normal conditions? Northridge triggered extensive research into steel moment connections and seismic design. Engineers tested connections, analyzed failures, improved details, changed design approaches, and strengthened the rules used for earthquake-resistant construction. Once again, failure became knowledge. Steel leaves the skyscraper. Here's something most people don't realize. Steel isn't just for skyscrapers. Look inside a warehouse, a factory, an aircraft hangar, a large sports or exhibition building. You may find a portal frame. Steel columns and beams can create enormous clear spaces without filling the building with internal supports. And because many steel components are fabricated off-site, they can arrive at the construction site ready to assemble. That means less site fabrication, greater precision, and potentially much faster construction. Steel is also increasingly used in modular construction, where building components or modules can be manufactured in controlled factory environments before being assembled on site. The skyscraper may be the symbol of structural steel, but steel quietly supports everyday life all around us. The steel building you don't see. And here's where steel construction gets even more interesting. The future isn't necessarily about putting more steel into buildings. It's about using it more intelligently. Steel components can be fabricated with high precision before reaching the site. Buildings can use modular construction, where three-dimensional units are manufactured and then assembled around a structural core or steel stability system. Steel can create large open spaces. It can support adaptable buildings. And because many steel connections can be dismantled, components can potentially be reused or recycled rather than simply demolished and discarded. This adaptability matters, because the buildings we construct today may need to serve completely different purposes tomorrow. An office might become housing. A warehouse might become a distribution center for a new industry. A building might need additional floors, new services, or a different internal arrangement. A rigid building can become a problem. An adaptable structure can become an asset. And steel is particularly well suited to this idea. Conclusion: the material that changed our cities. From the first iron bridges, to the Crystal Palace, to the world's first skyscrapers, to modern high-rise buildings. The story of structural steel is really a story of human problem solving. Iron showed us what was possible. Steel expanded those possibilities. Connections became stronger. Failures became lessons. And engineering kept evolving. Today, when you look at a skyscraper, you're not simply looking at glass and concrete. You're looking at a skeleton built from more than 2 centuries of engineering knowledge. And perhaps that's the greatest lesson of all. We don't simply build higher because we have stronger materials. We build higher because we learn how to use those materials better. Steel didn't just build the modern skyline. It helped humanity reach for it.